In this video, I want to demonstrate how to do a revolution joint in dynamic simulation. A revolution joint is probably the most common joint in a mechanism that has some sort of motion. Now, in the assembly environment, we can put a constraint between two objects. In this case, I have an insert constraint. You could also use one of the assembly joints, and I have 1 degree of freedom then on this that it rotates. Now, one thing that we need to consider when we're doing an assembly is that this is just a kinematic motion. It doesn't take into account forces, friction, gravity. In order to do that, we need to go into the dynamic simulation environment. And so I'll go into environments, dynamic simulation. And so I have then a revolution joint between these two parts. Now I'm going to start this in a very basic step-by-step way, and we'll go through all of the various joints. So if I go into this joint table, there are these joints such as revolution, prismatic, cylindrical, all of the various types of basic joints, and we'll go through each one of these, and then the rolling joints representative of gears, a rack and pinion, a cam, belt, and so forth. And then we'll look at the sliding joints and the 2D contact, and we'll probably start doing 2D contact early on, and also the 3D contact and spring dampener jack. Now, you may not see all of these joint types listed when you first open up dynamic simulation. So the reason you may not see that is that if you have turned on under simulation settings automatically convert assembly constraints into standard joints, it will not show you any of the standard types of joints in that table because they've already been converted from the assembly. And so in order to see all of the possible types of joints, you have to turn this off. Now normally we would leave this on, but to start out we'll turn this off, and then as we get more experience we'll normally leave this on. If I drag this, notice that there is a vector now attached to the part. The longer that vector is, the more force I'm putting on the part, and the shorter it is, the less force. So I have a direction and an amount of force. So that's different than just the kinematic motion. Now in this case, the part went right through each other, but we will also set that up so that when it comes over here and contacts that part, it will stop. Notice that we can also define gravity on our components. So because I'm not familiar with how much experience each user might have, I'm going to start this in a really very basic way where we're going to model each one of our parts even though they're really simple, and then as we gain experience, then I'll start giving you the more complex models. So let's look at how to get started on Autodesk Inventor Professional Dynamic Simulation. I'm going to start out a new part file, and so I'll select part. Now I'm going to do this one as inches, but I'll go back and forth between inch units and metric units on various assemblies that we do. I'll go to the top view and I'll right click on the top plane and I'll do a new sketch. Now I'm doing this in Inventor 2021, but it would work in earlier releases of Inventor as well. So I'm going to do a rectangle at the origin, and I'll go over to the right, and I want this to be 2 inches long, and I'll put in the height of it here in a minute. So I've got that as 2 inches for the distance from the origin. Let me turn on the visibility of that origin. So I put the origin in this location. I'm going to draw a circle now from here over to here, and I'll dimension the diameter of that circle as 0.5. I'll draw a second circle here, and I'll do the dimension of this circle as 0.27. Alright, so I have 2 circles and a rectangle. My sketch is fully constrained. Go to Tools, Application Options, and on the Part tab, set this display extended information after feature node name in the browser, so it tells me how far I extruded that. I also, on the sketch tab, I turned off the grid lines and the axes, but I do want to auto project the part origin on each new sketch. I'm going to do extrude, and I'm going to select this area inside those two circles. I'll flip that direction to go down. I also want to get this little piece right here and this piece right there. So I'll extrude that going down, and then I'm going to make that sketch visible again. And I will do extrude again, and this time I want to get this portion right in here and this profile in here, and I actually don't want this first part, so I'll control unselect that part so that I only have outside of the cylinder. I'll extrude that going up 1 inch. Then I'm going to put a fillet on this edge and this edge, so I'll do fillet on this edge and on this edge, and I will do that as 0.0625. I'm going to change the color of this part, and so I'll come up here to my colors, and I'm going to set that to a blue color, and I will save this file. Now I've already created an active project so that I know where my files are being saved. You should set up a project for your work as well, and I will save this as hinge leaf hole. Alright, then I'm going to save this as a copy, and so I'll do File, Save As, Save Copy As, and I'm going to call this hinge leaf pin. And then I'm going to open up the pin file, so I'll open up the pin file, and I'm going to then edit the first extrusion. And with profile active, I'm going to control select inside this hole as well, and so that closed off that hole. And let's change the color of this part as well, so I'm going to change this to a yellow color. Now you can use whatever color you want. Now I see that I missed that area right in there, so I'll edit that feature again, and I'll control unselect this area so that that is completely solid. And then I'm going to extrude this center circle coming up as a pin. So I will extrude again, and I'll select the circle, and I want it to come up 1 inch. And let's put these side by side. So this was the part with the hole in it. This is the part with the pin. And I want to make this a little bit bigger so that there's some clearance, and so I'm going to drag my end of part marker up under the second extrusion, and I'm going to move that face. I want to allow a little bit of clearance between these parts, and so I'm going to do thicken offset, and I will select this face, and I'm going to cut that. And I see the preview with it coming out in this direction. I want to go in the opposite direction, and I'll do that. I'll go ahead and leave that as 0.1 because I'm curious of what it's going to do up here based on the preview. So I'll say OK to that, and I see that it cut that away, but I don't want to go quite that far. So let me edit that feature, and let's do 0.005, and so I've made that a little bigger than this circle right there. And then I might get an error when I go to the fillets, so we'll drag this back down, but it resolved the fillets okay. And then on the pin, I want to make that diameter a little bit smaller than this 0.27, so I'm going to make that 0.265. When we make parts in the real world, we can't make perfect parts. There's always a tolerance associated with our features. So if I tried to make that exactly 0.27, some of them are going to be a little bit larger, some of them are going to be a little bit smaller, but if it gets larger, it may be too tight to fit into this hole. And so we need to allow appropriate clearances between our mating parts. We should think of that right up front. Now, Inventor won't care. Well, in some cases it will, in some cases it won't. If we try to model these as perfect parts, when we're doing dynamic simulation, we should consider realistic clearances between the parts. All right, I'm going to turn off the visibility of the sketch, and I'll turn off the visibility of the sketch on this component, and we'll save these. I need to save this one, and then we'll start a new assembly. And so I will do a new assembly. I'm going to go ahead and call this revolution joint, and so let me save it, call it revolution joint. And then I'll place the whole side, and I'm going to put it at the origin. So I'll right click, I'll tell it place grounded at origin, hit escape. So this part has no motion within the assembly. It would be attached to a door or something when we put it into a main assembly. I'll do place, and I'll put in the pin, and so here we see the pin, and now the pin is free to move around in space, where this part is fixed or grounded in space. Now there's several ways that I could constrain this. I could do a mate this face to this face, the axis of this pin to the axis of the hole. I'm going to do an insert, so I'll do constrain insert. You could also use the assembly joints. Now the assembly joints don't necessarily convert directly to a dynamic simulation joint. They may or may not. You would need to experiment with that to see how they work. I'll do an insert, and I'm going to insert this circle onto this circle. And then if I look at this, so we have a little bit of clearance in between here and here, we should. So when I look at it on this side, I see a little bit of clearance, but on this side I don't see the clearance, so we need to add that on this blue part as well. If I go into a section view, we see that we have a little bit of clearance between the hole and the pin, so let's go back and add the clearance for this part. And so I'll go back, and remember we went up to the second extrusion. We did a thicken offset of this face, and I see that it's coming out this way. I want to go in to cut away, and I'll do that 0.005 to cut that clearance, and then I'll drag my end of part marker down, my fillets update, I save it, I go back to my assembly, I check, and I see that a little bit of clearance here, and I have the clearance here, and then the clearance between the pin and the hole. Let's do one more thing on this. On this pin, I'm going to take the paint off of these faces, and so I will right click on one of these faces, and I'll go to properties, and I can select a flat color, and if I want to copy that, an easy way to do that is I'll click on adjust, and I'll with the eyedropper I'll pick up that color, and then I get a paint bucket. I can drop that paint color onto here, and I'll drop it onto here as well. And whoops, I got the whole part, so I want to control unselect part, and let me get this face. So I held the control key down to get multiple faces, and I'll accept that. So I took the paint off of those faces, and I may want to do the same thing on this part, and I'll right click, and I'll go to properties, change that to a flat aluminum color on that hole, and then I'll do the adjust. With the eyedropper I'll pick up that color, with the paint bucket I'll drop it on that face, just so we can clearly see those faces as different colors. Now if I drag this, I see that right now it's not moving. If I right click on, notice there's a lock symbol on this insert constraint. So if I edit that, the last time I did an insert, I had it to lock the degrees of rotation. And I actually want this to be able to rotate, so I'll unselect the degree of rotation, and so now I can rotate this, and then we will go into dynamic simulation. So I'll go to environments, into dynamic simulation, and it automatically converted my assembly constraints into a revolution joint. Now sometimes when you use a insert constraint, it won't automatically convert that, and I'll show you how to overcome that issue in a future problem. Let's go to our simulation settings though, and I'm going to turn off this automatically convert constraints to standard joints. Now it says, do you want to keep those? Normally I would say yes, the joint that it created? I would normally say yes, but in this case I'm going to say no to do that. Actually, let's cancel out of this for a minute. If I go to my joints and go to the joint table, here's the category for standard joints, but it doesn't show the revolution joint. And remember, there are a whole bunch of standard joint types that are normally populated in this table. So we don't see that because we have it set to automatically convert assembly constraints to joints. So I'll turn that off, tell it no, in this case not to keep that. Notice it's showing our two parts as being in the grounded group. But let's go back to this insert joint, and I'll go into the standard joints again, and this time notice there are 10 different standard joints here. We want to do a revolution joint. Now it gives you a preview picture of the degree of freedom that would remain, in this case 1 degree of freedom revolution, but it could be any type of mechanism that has a degree of freedom as revolution, so it doesn't necessarily have to look like this picture. This is just representative. So it asked me to select component number 1. I will select this cylinder, and then I can set an origin if I like. I could put that origin up here, although it'll usually automatically define an origin. I'll go ahead and select that circle. Notice it moves the coordinate system up to that center of that circle. The X is a single arrow, Y is a double arrow, and Z is triple arrow. And so if you needed to flip the X or Z, you could do that here. I'm going to go to component number 2, and I'll select this cylindrical face, so it has to be a cylinder for the revolution joint. I'll select this circle, and I'll say OK to that, and again I could flip that Z to match those Z's up, although it will do it automatically when I select OK. I could put the origin down here, and then it's going to line up the X's and the Y's. If I flip this, it will move less, so it's going to line up this X with this X. I'll say OK to that, and now when I drag this, I see the revolution joint. So that was manually applying the joint, the same as would have happened automatically. So that was our most basic joint, the revolution joint 1 degree of freedom. If we come over here now under our grounded groups, before this part was in the grounded group, now only this grounded part, and then under mobile groups is this hinge leaf pin, and we have 1 degree of freedom revolution joint. If I right click on this and I go to properties, and we see that on this degree of freedom 1 tab, it has 1 degree of freedom revolution, and we can set in a position here, and later we'll go through and manipulate a bunch of these tools within the revolution joint. Notice that when we drag this part, it goes right through the other part, and so we want to set this so that it stops when they come in contact. Now this face is stationary. This face moves, but it stays in the same plane. Same way down here, this is stationary, this face moves, but it stays in the same plane. So we can do this, because that stays in the same plane, we can do this as a 2D contact. So I'm going to do insert joint, and I'll select the 2D contact, and I'll select this face, and it'll find that loop curve that's going around that face. So I'll select that face, and for the second curve I'll select this face, and it finds that loop going around that face. I'll say OK to this, and now when I drag this part, when it comes over here, it stops when it comes in contact. Notice if I come against it hard, it bounces just like the real world. So I'm going to delete that contact, and instead let's say that I wanted to use this face and this face, but notice this one has a hole in it, where on this side there was no hole in either of the faces. So I'll do that 2D contact again, and I will select this face. There's no issue with selecting that one, but I'll select this face, and when I do, it comes up with a second option here asking me to select an edge, because I could either select this boundary on the outside edge, or I could select this whole boundary. Now of course for this one we want this outside boundary, and I'll select any one of these edges on that boundary. So I'll select that edge. If I had selected this face first, this tool would have come up over here. So I'll select that edge. That defines the boundary that I intended to set the contact with, and when I drag this part again, when it comes over there against this, it stops. if I come all the way around to the other side when it gets to where it would contact. Now if I go too fast, the computer can't keep up with the calculations and will give me an error. And sometimes you can end up with, I have this part now embedded inside of this part, and so I have to get out of that error condition. There are two ways I could do this. I could undo back to where it wasn't into an error condition, which would be the easiest way, or I could temporarily suppress that joint, move my part to where it isn't in an error condition, and then unsuppress it. And so now, as long as I don't go too fast, I'm okay. And we'll see later on, it's best to not drag it with the mouse, but put it under the computer's control, and you won't get an error where it can't keep up with the calculations when it's under the computer control. So that is the revolution joint and with 2D contact. One last thing that I need to point out on this again is we see this bounce when it comes in contact. And if I go back to the assembly environment, and I could add these two parts to contact set. So I could add this part and this part to contact set, and then under the inspection tab activate my contact solver. So I'll leave it off for a minute. And so I drag this and it goes right through, and then I activate the contact solver and I drag this and it stops, but you don't get that bouncing that may occur between real parts that we see in dynamic simulation. It just stops when it comes in contact. Well, one final thought is I added this fillet in here. So before we had a fillet up here and here on both of these parts, but then I added this fillet and this fillet, and if I go into the dynamic simulation, it automatically updated that boundary for the 2D contact. So I had gone back to each one of these parts, and I edited this fillet, and I added the fillet here and on the mating part.